Today we'll be talking about the chemical kinetic importance. First of all, the rate of any chemical reaction is change in the concentration of the reactant or the product with respect to the time. This rate of reaction can be expressed in two different ways. Either it can be expressed as average rate of reaction or the instantaneous rate of reaction. When we talk about the average rate of reaction, we just decide a time interval, and during this time interval whatever the concentration changes occurs, we talk about it. For example, if I consider the reaction R is changing to P, reactant is turning to the product, then I want the rate of reaction between the time interval T1 and T2. Then that I'm talking about the average rate of reaction, that will be equals to the change in the concentration of reactant. Now this is between T1 and T2, so the time interval is T2 minus T1. We are talking with respect to R, so I need to write the minus sign, which is indicating decrease in concentration of reactant. So let's say at T2 the reactant concentration is R2, and at T1 the reactant concentration is R1. So overall this can be calculated like this. So this is nothing but minus delta R, that is change in the concentration of reactant, upon delta T. But if I'm talking about instantaneous rate of reaction, I want it at the particular time at T is equals to 0. So it can be the R instantaneous, that will be equals to dR upon dt. Minus sign indicates decrease in the concentration. So always we have to remember the rate of reaction always increases with decreasing concentration of reactant, and rate of reaction increases with increasing concentration of the product. So if we plot the graph of rate versus the concentration of the reactant, the concentration of reactant is expected to decrease while concentration of product is expected to increase. We can talk about the next term, that is rate law. If we have an equation like A plus B is giving me twice of AB, then the rate is directly proportional to A raised to X and B raised to Y. These are the X and Y, these values to be calculated from the experimental data. So the rate is equals to K into A raised to X and B raised to Y, where K is called as a rate constant, and overall order of the reaction, which is to be calculated by adding these exponents. So we have overall order over here, X plus Y. Now in the case of order of reaction and the rate law, we related to the K, we can decide the order of reaction. For example, if N is equals to, that is order of reaction is equals to 0. If N is equals to 0, that is 0 order reaction. If it is 0 order reaction, the K has unit mole per liter per second. If we have N is equals to 1, this is your first order reaction, then the K has unit second inverse. If it is N is equals to 2, then it is second order reaction, then the K has unit that mole per mole liter per second. If N is equals to 3, that's your third order reaction, so it is mole minus 2 liter square minus 1. So overall the unit of K for any order of reaction can be decided like this: mole per liter raised to 1 minus N per second. So if you have N, let's say, is equals to 0, so this is 0, so it's L mole per liter per second. If it is 1 minus 1, this raised to 0, that means it is 1, so per second. If it is 2, that is 1 minus 2, it's minus 1, so mole raised to minus 1, this is minus 1, and this is plus 1, that will become 1, and here it is minus 1. So from the value of K also we can decide the order of reaction, or if you know the N value of N, then we can decide the unit of the K. So from the K order, generally MCQ is related, you should know both the way. If you know the value of N, you can decide the value of unit of K, and from the unit of K you can predict the order of reaction. The next term which is very important is the molecularity of reaction. When we talk about the molecularity, is the number of molecules which are actually participating in the chemical reaction. For example, if twice of HI is giving you H2 plus I2, here two molecules of HI is undergoing the decomposition so as to give the H2 and I2. So I'll call this reaction as bimolecular reaction. If I talk about twice of NO plus O2 giving me twice of NO2. So here two molecules of NO and one molecule of O2. So total three molecules are participating in the reaction. So I will call the molecularity over here is 3. Next part, we are going to talk about the most important part of the chapter, that is integrated rate law. Integrated rate equations are the simplified form of the rate laws which are made convenient for the calculations. Now when we talk about the different types, let's talk about different order reaction, and related to that we'll talk about its rate equations. Now in the case of, let's say, zero order reaction, their rate equation, we know the rate for the zero order reaction is independent of reactant, so I will write K into Rs to 0. So this is indicating this particular reaction is independent of the rate law. So for this, if I have to calculate the integrated rate law, so integrated rate law for this is concentration of A will be equals to minus K into T plus concentration of A0. This is the integrated rate law. So we can plot the graph of over here, concentration of A versus concentration of T. So when you plot this graph, this is indicating the negative slope with some intercept on the y-axis. So graph will be like this. So slope will give you idea about minus K, and this intercept will be A0. So this is related to the zero order reaction, and in case of the zero order reaction, one more term we should remember, that is nothing but T half. The T half for the integrated rate law is nothing but the concentration of the reactant divided by 2K. If we talk about the first order reaction, for the first order reaction, the rate is equals to the concentration of reactant. If you just make its integrated law, then we have equation log of A is equals to minus KT upon 2.303 plus log concentration of A0. So here we'll be plotting the graph of the log of concentration of A versus T. So here the value of slope will give us the value of minus K upon 2.303, and the intercept will be the log of A0. Here value of T half, we should know it's minus K upon 2.3, it should be T half should be equals to 0.693 upon K. In case of second order reaction, the rate is equals to K R raised to 2 because it's a second order. So if you integrate this, 1 upon A will be equals to minus KT upon 2.303. It's plus KT upon KT plus it's upon 1 upon A0. So if you plot the graph of 1 upon A versus T, 1 upon A versus T, this will be positive slope, and the positive slope will give us idea about the K, while this intercept on the y-axis, it's 1 upon A0, while the T half for this is 1 upon K into concentration of A0. So overall T 1 upon N, that is the time required for the nth fraction of any order reaction, it's 2.303 upon K log 1 upon 1 minus 1 upon N. This formula is to be remembered while calculating the MCQ related. If you want to calculate the time required for any nth fraction, any nth type of the decomposition, you should remember this. Also, there is one more formula that T half, always remember, is directly proportional to the concentration of A0 raised to 1 minus n. Or you can say this is T half is equals to or directly proportional to 1 upon, just make it reverse, so concentration of A0 n minus 1. So these two formulas to be remembered, any one formula from this and this to be remembered for the calculation. So overall this is a comparison for the zero order, first order and the second order. For the MCQ purpose, at least you are supposed to remember the formulas related to the second order reaction. Now, temperature dependency on the rate constant, that is, in short, we are talking about the relation between the K and the T. Now, this is being given by the Arrhenius equation, which says that K is equals to A e raised to minus EA upon RT, where A is the Arrhenius constant. If you just take the log on both sides, finally you will get the equation, that is log of K is equals to log of A minus EA upon 2.303 RT. This is called as the Arrhenius equation, giving the relation between the K and the T. Now, if you are comparing the equation or the rate constant of the different temperatures, then we have equation log of K2 upon K1 is equals to EA upon 2.303 R into bracket 1 upon T1 minus 1 upon T2. So this equation we have to remember while calculating the MCQs related to the rate constant at the different temperatures. Now, when we talk about the radioactive disintegration reactions, they are generally first order reactions. Overall, we have to remember the disintegration is the infinity, and therefore the term average life is generally used. Average life is denoted by a symbol tau. Now, when we talk about the tau, tau is always calculated as one of its reciprocal of the K, disintegration constant. So we know that K is equals to 0.693 upon T half. So this is T half upon 0.693. So it is, in short, the tau is equals to 1.44 into T half. The tau, again I am repeating, this is called as the average life. So average life for any radioactive element is to be calculated. We have formula 1.44 into T half. Also, we have to remember the time for the zero order reaction to get completed. So time taken for the zero order reaction for the completion that we can calculate, that is T 100% is always equals to the concentration of A0 upon K. So these are the formulas we need the extra, that is for miscellaneous numericals or the problems. We can just remember these formulas. Next, we are going to talk about the average activation energy. When we talk about a particular reaction, there is a reactant with certain amount of energy. This reactant has to gain certain amount of energy to reach to the transition state. The amount of energy that reactant gains, that is the energy difference between the transition state and the reactant, we call it as the energy of activation. And then that is turning to the product, that's a final reaction. Now when we talk about